Hello students. Now in this video we will discuss about the next application of Ampere's circuital law, that is a magnetic field due to a toroid. What is toroid? Toroid is a endless solenoid. Let us suppose this is the solenoid, and if you bend it in a circle, then it will become a toroid. Very simple. Just bend in a circle solenoid. So just bend the solenoid into a circle. That shape you will you can call that is toroid. You can also say that endless solenoid. I hope you are getting. Let us suppose this is the endless solenoid. Okay, endless solenoid, or this is the, you can say this is the toroid. Okay, this portion empty space, this empty space is called anterior to the toroid, and this portion, this outer space, is known as the exterior to the toroid. Inside, what is inside? Inside is in between this is this the inside toroid, and we have to calculate magnetic field at these 3 points due to this toroid. Okay, hope you are getting. Okay, let us draw the structure. This is the solenoid, endless solenoid, simply toroid. If you cut it, you have cut like that in the solenoid, like that. If this is bend, and cut it from this one portion, take one portion and remove second portion. Okay, this portion, back portion we have taken, and after that the structure will be like that. One wire, okay, this is the wire, okay, hope you are getting. This is the first wire, second wire, first wire, second wire, first wire, second wire, this like that. Okay, if the current is going into the plane, current is going into the plane, and after that it will come back from that, means in these wires current is into the plane, and from that wires, means outside wires, the current is out of the plane. Okay, and we have to calculate magnetic field at interior. Let us suppose this is the center. Okay, and we have to calculate magnetic field in the interior at any point. Let us suppose this is the interior point. Let this is the R from the center, and just draw a Ampere circuit as you have used in previous lectures. Apply Ampere circuital law. What is Ampere circuital law? Ampere circuital law is line integral of magnetic field is equals to mu naught times net current. Okay, apply. What you will have, that magnetic field is equals to line integral of dl. You know that magnetic field is constant. It can be taken out, is equals to mu naught times net current. This is the tough work. This is a tough task to calculate net magnetic field. Rest of the things is easy, but only tough task is just to calculate net current. What is the net current threading that particular area? Think. No current is threading that particular area because all the currents are outside the particular area. That means net current is 0, then magnetic field is 0. Means in the interior point to the toroid, magnetic field is 0. Next point, that is interior. That is inside. And just to calculate the magnetic field inside, let us suppose this is the point that is inside the toroid. This distance is, let us suppose, capital R, and draw a Ampere's circuit. This is the Ampere's circuit. Okay, you know that magnetic field is constant. dl is equals to mu naught times net current. What is net current? If total number of wires in the toroid is n, then only this portion, these wires, not these wires, only these wires is threading that particular area, that area that is enclosed by the Ampere circuit. Only these wires threading that particular area. That means current through these wires, these 8 wires, will be considered. Okay, if these wires, and this is the n number of turns, if there is a n number of turns, that means total current threading that area will be capital Ni. Integration of dl is 2 pi r. B into 2 pi r is equals to mu naught times Ni, and B is equals to mu naught into capital N upon 2 pi r into I. This is the formula for the magnetic field. If small n is the capital N upon 2 pi r. In the solenoid we have taken capital N upon L because the solenoid was long and total length was L. But in toroid the total length is, you can say that the solenoid is equals to the circumference. Total number of length in the solenoid, you can consider in the toroid total length and total length in the solenoid. This is the total length in the toroid. Total length means circumference. Means you can say that total number of turns per unit length. Total number of turns per unit length is called small n. In place of capital N upon 2 pi r, you can write B is equals to mu naught N upon 2 pi r N into I. You know that magnetic field due to a toroid, inside the toroid is equals to mu naught times Ni, and you know that in the solenoid lecture we have studied that B is equals to mu naught times Ni. This is the formula. Both the formulas are same, but N in the solenoid is L upon N. In toroid this is N upon L, and this is N upon 2 pi r. In the toroid N upon 2 pi r, in the solenoid N upon capital L. Both are length. The formula is same, but where formula for small n is different. Hope you are getting. And last point, that is magnetic field at the exterior. Magnetic field at the exterior point. One point is there. Let us suppose this is the capital R, and first radius means inside radius. Inside radius is, let us suppose, R1, and outside radius of the toroid is, let us suppose, R2. In place of R you can write R1 plus R2 upon 2. Average radius will be equals to the radius of the toroid, average radius of the toroid. Okay, if in the question only a radius of the toroid is given, then in place of R you can use directly. But if inside and outside radius is given, just take average, and that average will be used as a radius of toroid. Okay. Next point, that is we have to calculate magnetic field at the exterior point. Magnetic field at the exterior point. Let us suppose this is the exterior point, and first point is just draw Ampere's circuit at that point. Ampere circuit, and radius from that is, let us suppose capital R. Okay. This is the radius. Just apply the Ampere's circuital law. B integration dl is equals to mu naught times net current. What is net current? Net current threading that area. What area? Which area? Area is that whole area, this area. Okay, whole area. Simply you can say, let us suppose this is the whiteboard. One, this wire, if from these wire current is going into that plane, and from these wire current is out of the plane. Means this plane is cut by these currents and these currents, but the number of wires threading in this direction and threading in this direction, both are equal. That means equal amount of current is crossing this particular area and this area. Means same amount of current is crossing in this direction and this direction. That means the net current passing through that area is equals to 0. The net current is equals to 0. Magnetic field is equals to 0. Means exterior to the toroid. Magnetic field at the exterior to the toroid is 0. Hope you are getting this formula. And magnetic field outside or exterior to the toroid is 0. Hope you are getting my points, and thanks for watching this video.